Today's topic is high-pass filters. The definition of high-pass filter is a filter which passes only these signals whose frequencies are higher than the cutoff frequencies, thereby attenuating signals of lower frequencies. The value of cutoff frequency depends on the design of the filter. The amount of attenuation for each frequency also depends on the filter design. High-pass filters have many uses, such as blocking DC from circuitly sensitive to non-zero average voltages or radio frequency devices. Image and audio sharpening also uses high-pass filters. They can also be used in conjunction with low-pass filters to produce band-pass filters. The basic high-pass filter is built by series connection of capacitor and a resistor. While the input signal is applied to the capacitor, the output is drawn across the resistor. In the circuit arrangement, the capacitor has colossal reactance at lower frequencies, so it acts as an open circuit to the low frequency input signals until the cutoff frequency is reached. Filter attenuates all the signals below the cutoff frequency level. At frequencies above cutoff frequency level, reactance of the capacitor becomes low and it acts as a short circuit to these frequencies, thereby allowing them to pass directly to the output. The transfer function of this LTI system is SRC over 1 plus SRC, and the cutoff frequency is found by 1 over 2 pi RC. The phase shift is the arctangent of 1 over 2 pi FRC, and the gain is V output over V input. As we can see here, at low frequencies, the XC goes to infinity, so the output is 0. And at high frequencies, the reactance is 0, so the output is equal to the input. Here's a really quick example of finding the cutoff frequencies. Taking these values and plugging them into 1 over 2 pi RC, we get 2.8 kilohertz. In high-pass filter, all frequencies lying below the cutoff frequency are attenuated. Here the bandwidth of the filter denotes the value of frequency from which signals are allowed to pass. For example, if the bandwidth of the high-pass filter is given as 75 kHz, it means that the only frequencies from 75 kHz to infinity are allowed to pass. The phase angle of the output signal is plus 45 degrees at the cutoff frequency. The formula to calculate the phase shift of the high-pass filter, as denoted before, is the arctangent of 1 over 2 pi FRC. In practical application, the output response of the filter does not extend to infinity. The electrical characteristic of the filter elements applies the limitation to the filter response. By proper selection of filter components, we can adjust the range of frequencies to be attenuated, the range to be passed, etc. An RL circuit acts as a high-pass filter when constructed as in the circuit shown below. The resistor is the series component and the inductor is the shunt component, and the cutoff frequency is R over 2 pi L. The filtering action of the circuit in the figure is a result of the inductor's response to the decrease in operating frequency. As the reactant curve indicates, the bottom left picture, the reactance approaches infinity as frequency increases. If the input frequency decreases to 0 Hz, the inductive reactance decreases to 0 ohm. Ignoring the small amount of winding resistance in the coil, the shunting inductor is represented as a shortened path to the ground, in which case VRL is 0 volts. If the input frequency to the circuit increases, the reactance of the inductor increases until the component effectively acts as an open circuit. If we assume that the reactance is infinity, as you can see, the inductor is represented as a break in the shunt component path. In this case, VRL is E minus VRF. Here's an example of finding the cutoff frequency of an RC high-pass filter. First, the circuit resistance is found as R equivalent RF parallel to RL, and the value of it is 69.3 ohms. Now, the cutoff frequency of the circuit can be found as 1 over 2 pi RC, and this R is are equivalent, and plugging the numbers in we get 230 Hz. The frequency response curve for the circuit is shown below. This result indicates that the power gain of the circuit is reduced by 50% of its maximum value when the operating frequency decreases to 230 Hz. Now for an example of an RL high-pass filter. First, the circuit resistance is found, and then now the cutoff frequency is R over 2 pi C. Then plugging the numbers in, we get 305 Hz. This result indicates that the power gain of the circuit is reduced to 50% of its maximum value when the operating frequency decreases to 205 Hz. The frequency response curve for the circuit is shown. Active high-pass filters, unlike the passive high-pass filters which have an infinite frequency response, the maximum passband frequency response of an active high-pass filter is limited by the open loop characteristic or bandwidth of the operational amplifier being used, making them appear as if they are bandpass filters with a high frequency cutoff determined by selection of op-amp and gain. Here's a quick review. A high-pass filter is an electronic filter that passes signal with a frequency higher than a certain cutoff frequency and attenuates signal with the frequencies lower than the cutoff frequency. The capacitive high-pass filter inserts a capacitor in series with the load, whereas an inductive high-pass filter inserts a resistor in series with an inductor in parallel to the load. The former filter tries to block unwanted frequency signal, while the latter tries to short it out. The ideal characteristic of a high-pass filter are shown right-hand side. The passband is referred as the high-pass filter allows the higher frequencies that are greater than the cutoff frequency. The filter attenuates all the low frequencies, which are referred to as the stop band. Application of high-pass filters. The high-pass filter applications mainly include the following: speakers for amplifying signals, image and audio processing, amplifying DC current and AC coupling, control system, DLS, splitters in telephones, and RF applications. The high-pass filter in image processing is high-pass filters are used in the image processing for sharpening the details. By applying the filter over an image, we can exaggerate every tiny part of details in an image, but overdoing that can damage the image as these filters amplify the noise in the image. High-pass filters used in digital image processing to perform image modification, enhancement, noise reduction, etc. These two pictures shows the edge detection using high-pass filters. An audio high-pass filter is an equalization tool that attenuates all frequencies below a set point. In other words, high-pass filters remove low frequencies while allowing high frequencies to pass through. They are used in almost every application of audio technology. High-pass filters are often used in studio recording and sound reinforcement to attenuate extra noise, low-frequency content like mechanical rumble or vocal plosives. By choosing a filter with a cutoff frequency below the fundamental frequency range of the program, a high-pass filter can be used to differentiate between program signal and low-frequency noise. The following image shows a frequency response graph of a pink noise. Every octave is evenly represented, forming a straight line from 20 Hz to 20 Hz. The next image shows the same pink noise after being processed through a high-pass filter set to 500 Hz. The frequencies above 500 Hz are unaltered, but the frequencies below 500 Hz are being attenuated. Thanks for watching this video.